about that. So yeah. So the zeroth law tells us that the zeroth law implies that there is something called temperature. And when the temperature of two systems are the same, they are in thermal equilibrium. Okay. All right. So before we move on to the next thing, let me just introduce some more concepts. Okay. Any more questions, by the way? So this proof is taken from David Tong's lecture notes. Okay. So and it's a very nice. This is the kind of style of argument that old school thermodynamics used, right? Very sophisticated mathematical argument that didn't need to talk about what was, so physicists came up with the idea of energy, came up with the idea of pressure, came up with the idea of entropy before they were certain that things were made out of molecules. So these are amazing achievements. So I think that it's good that we review these achievements in a style of argument which is kind of old-fashioned. And that's what I'm doing, okay? Of course, after this, we will see what's under the hood, right? That's what statistical mechanics does, is that it takes this beautiful, old school, Mercedes automobile and opens it up and you see underneath, how it's made out, what are the mechanics, right? So, okay, so our next idea that I want to is what is a state variable? I've kind of mentioned it, but haven't really. So a state variable is an independent variable, a set of that is part of the description of the state of the system, right? So for example, we can choose that to be for the gas P and V. So there are other variables, say that select T, but that's not independent of P and V. So now we define a function of state. So, a lot of thermodynamics is about quantities which are functions of the state variables. And for example, we will deal with entropy, we will deal with energy. These are all functions of the state. So what is a function of state? Very easy. It says if, say, x1, x2, ... xn are your independent state variables. Independent is redundant here, but I'm writing it anyway. State variables. Then any function of it is a state function, is a function of state. This is a mathematical triviality, but it's kind of an important triviality, is that a change in a function of state, it's given by, say, d of f integrated over some initial and final value of f. And that's given by, say, f, say, x1 prime ... xn prime minus f, say, x1 ... xn. So if I have the state space here, and I have so let's just call this x1, this is x2, and this is some initial point, and then this is some final point, so this is 0 and this is 1, and then we change the state. So the value of the function here is f of, say, x1, x2, and the value of his here is x1 prime, x2 prime. So the idea is that the change of a function of state only depends on the endpoints of the state, endpoints of the, so if you start a system here and you somehow change the system so that it ends up here, so you start the system here and you say change the pressure and the volume such that it goes via this path, ends up here, then the change in f will only depend on the initial point and the final point. It will not depend on the path that is taken, right? That is basically what we are saying. So what does it mean? What it means is that on an infinitesimal scale, so if the change is infinitesimal, for an infinitesimal change of, say, the state variable xi, d of f, that is the change in the function of state, is an exact function. Is an exact differential, sorry. Right. Is an exact differential. Okay. Do you guys know about the difference between what is an exact and inexact differential? Did everyone leave?
I do, but I don't want to speak for everyone.
Okay. Anyone else?
I mean, might as well talk about it.
Yes, sir, জানি কিন্তু মানে এটা আবার শুনতে সমস্যা হবে।
হ্যাঁ, শুনতে তো হবেই। হ্যাঁ, okay. Let's. So exact differential is something. Suppose you have a function. So let's take an example, two-dimensional example. Okay. So we have a function, say f of x, which is x times y. So if I now take the exterior, the derivative of it, Leibniz rule tells us that we are going to get y times d of x plus x times d of y. So this is an example of an exact differential. Okay. On the other hand, we can take an example of a differential which is not exact. And in thermodynamics, we use the notation like that because they're small, but they are not exact. That is, there is no such function g such that by applying the derivative operator that you can get to there. So g doesn't exist. So del of g is basically, for example, if I write, say, x of d of x, then that's an inexact differential, right? So sorry, not that. Sorry, what I meant is this. Y, right? So this is an inexact differential. So there is no such function as g. G doesn't exist such that if you take the exterior derivative of g, you get this, right? So these things don't exist. So this is an exact differential. It's also called an exact form. So this is an exact differential. Okay. And this is an inexact differential. So, this guy by itself is an inexact differential. This guy by itself is an inexact differential, but together they are exact. And you can show that, well, basically, if it's very easy to show that, if you have an exact differential and you integrate it over some path, suppose the path is, say, from 0, 0 to, say, 1, 1. So we have the xy plane here. Sorry, this is not very straight. So this is x, this is y, and I'm starting from, say, this point, which is the 0, 0 point, and I'm, say, getting to 1. So this is the 1 point. And we can go to it in many different ways, right? So, for example, let's take the path where you go like this, right? And then there's another path where you can go like this, and then you can go like this. And you can show that, for this guy, the result of the integral, so this is path number 1, this is path number 2. So the result of the integral, doesn't matter whether you take path number 1 or path number 2. Okay? Now, whereas if I were to do this integral, then the result of the path would matter whether you go in this way or that way. Okay, I'm going to leave this as an exercise for you to do, okay? This is fun. This is very easy. Just do it for the simple setting, okay? For the simple setting, for the simple functions. All right? Okay, good. Right. So that was 2 types of, that was exact and exact integral. Now we want to discuss 2 types of state functions. So one is extensive state functions. So what are extensive state functions? These are state functions, so functions of state variable, which depend on size. So these depend on the size. These depend on the size of the system. Right, so for example, it could be, volume itself is a state function. It's a trivial function, but it's a state function. Say volume, so mass, the total mass, say the total energy, right? And then if you're looking at magnets, the total magnetization. And then there are intensive state functions. And these are localized state functions. So for example, which are not dependent on the size of the system, not localized, sorry, because we are assuming homogeneity, right? So non-dependent or not dependent, not dependent on the size. So for example, pressure, temperature, say density of the fluid, energy density, And what is pressure? It's just like force per unit area, right? So it's a kind of force density. And then, magnetic field, which is a localized quantity. These are intensive quantities. Okay. So I know that a lot of you probably have classes at 6:30, right? Is that true?